next component of what I'm going to talk about are different ways of representing effect sizes, and why we use effect sizes and p-values, except when we need to use the combined significance level meta-analysis. So essentially, there are three main classes of effect size indices that we might be interested in. We might want to, for example, if we have a groups as our on the independent variable side, but a continuous outcome, then we would use a mean difference, or either an unstandardized or a standardized mean difference. So if, for example, we were looking at the treatment group and a control group with an outcome of pain intensity, which is continuous, some people might choose to dichotomize pain and to pain or no pain or intense pain versus other. But in general, it's better to, if you actually have a continuous variable, it's better to leave it as a continuous variable than to artificially dichotomize it. Then we have true dichotomies. These are often used in biomedicine. So treatment versus control, and tumor recurrence versus non, or alive versus dead is usually a true dichotomy, except for vampires. And correlations are used when both variables are continuous. So age and number of words you can retain after some of the peaks come to you. But we also use things like prevalence, and we saw prevalence at the PTSD study, or we could look at means in a single group and how that might be useful. Okay, so I'm going to start talking about continuous data where we're interested in actually mean differences across two different groups, and I want to make the distinction between a raw mean difference, which is generally represented by an uppercase D, and the standardized mean difference, which is either going to be a lowercase d or an adjusted, a bias-adjusted mean difference, which is generally called G, or sometimes it's called Hedges G. So the raw mean difference is very simple. It will be the mean of the first group minus the mean of the second group. So let's say we're looking at some kind of aptitude test, and the mean, the treated group is 550. Let's say they were the tutored group, and then people who took the test cold had a mean of 500, so the mean difference would be 50. Raw mean differences can only be synthesized if they all represent or the same underlying scale. So, for example, if we're always looking at blood pressure, and blood pressure is going to be measured the same way from scale to scale, then we could use a raw mean difference. However, in most cases, when we're using means, people will either have used different scales of measurement, or they're concerned that there might be different degrees of variability in across the studies. So in that case, we want to standardize, and essentially we standardize the mean by dividing it by the pooled within group variance. So if the variance was 100 and the mean difference is the same as before, we would have a standardized mean difference of 0.5, which again, as I mentioned, would mean that a person at the mean of the treatment group would be half a standard deviation higher on the outcome scale than the person at the mean of the control group. And in general, that's considered a pretty substantial difference. So if, just as a short guide of when to use the raw versus the standardized mean difference, in order to use the raw mean difference, 3 conditions need to be met. The scale has to be either a natural scale or a known scale, which means a scale with known properties. All studies have to use the same scale, and the standard deviation scores has to be consistent from study to study. If you can't meet all of those conditions, you have to use a standardized mean difference. The difference between D and G is that G adjusts D for small sample bias. And the only time that it really makes a difference, whether you use D or G, is when you're routinely dealing with sample sizes of 10 or fewer. However, for consistency's sake, we generally recommend that you use G all the time rather than using G when you have a really small sample and then using D otherwise. And also, we're encouraging people to use G so it's just more consistent across the literature. But in practice, it doesn't make a difference most of the time.
Sorry, what in the case of negative values? So if we have a change in opposite direction?
Well, then it would be minus.
So that's you just put minus and that's okay, although it's in opposite direction.
Well, what you want to do is you want to make sure that a plus or a minus sign on your effect size always represents the same in terms of the treated group doing better, for example. So if you're measuring pain, and some studies measure pain and other studies measure pain relief, if you left them in their natural form, you would have both positive and negative effects, depending on whether the scale measured pain intensity or degree of pain relief. So what you want to do is you want to flip the signs around for those where, to make them logically consistent. But, but if in fact some things make your treated group worse, then it would be reflected in a true minus sign. And I think often those are particularly important to know about when we're trying to look at the variability of the true variability of effects, because if some effects are positive and others are truly negative, then it makes interpreting the mean very dangerous and misleading. You want to be careful there.
Yeah, there have been examples in talker reviews where it was extracted the wrong way around. Like a 0 would be no pain in some scales versus 10 maximum, and then it was switched.
Yeah.
And the extractors didn't realize that the negative,
Yeah.
the opposite direction of the scale. So I think there was a case where it was actually published and had to be retracted.
Yeah. Well, that happens when people use different scales, and some of them are sort of reversals of the other. And it is important to be very careful about. Our software, you actually have to indicate every time you enter an effect size whether it's positive or negative, so that you keep track of that. And if you want it to be sort of what you see is what you get, there's a feature that just says automatic, but it could get you in lots of trouble if you don't intend to. Okay. Should I talk about binary outcomes, or I put this in here sort of optionally, but since I find that people get odds and risks mixed up, I wouldn't think such a bad idea. Okay, so I want to talk about what risk is. I want to talk about what odds are. Then I want to talk a little bit about the difference between the risk difference and the risk ratio and the odds ratio, and talk about why Cochrane tends to like the risk difference, and what some of the things you need to keep in mind if you're using the risk difference. So here's a table on top. Okay, we'll call events in the treated group A and non-events in the treated group B, events in the control group C, and events in the and non-events in the control group D. And on the bottom, you can see that in the treated group you have 100 and 100 in the treated and control groups. In the treated group, you had 5 dead at the end of the study and 95 people that were alive. In the control group, you had 10 deaths and 90 people staying alive. So I'm borrowing from Cochrane's training materials here because it's really a very clear explanation as far as I'm concerned. So risk means you're interested in the number of people who have the event compared with the total number of people who could have had it. Okay? So if 100 people ate tuna fish sandwiches at the company picnic and 10 of them got food poisoning because the sandwiches were spoiled, then your risk would be 10 over 100. Okay? Or in this example, 24 people drank coffee, 6 developed a headache. So the risk of developing a headache, given coffee drinking, okay, that's an important condition here, so it's not the risk of food poisoning in the general population or the risk of headache in the general population, but given the treatment of tuna sandwich or coffee, and I'm using the word treatment loosely, okay, would be 6 out of 24 people or 25%. So the risk is the number of people who got it versus the total number who could have had it. Odds is a comparison of the number of people with versus the number of people without. So in the example of the coffee drinkers, if 24 people drank coffee and 6 people developed a headache, then the odds of developing a headache would be the 6 people who developed it compared with the 18 people who didn't, or 1 in 3. And I hate to say like 33% because that confuses things, but in this particular example, you can please forget this after a minute, after I point out that you can see that in one case it's 1 out of, the risk is 0.25, but the odds are essentially 0.33. Okay? So same data, same question, framing matters. Okay, so the whole point of this discussion on binary data is how the choice of an index really matters, and you have to think carefully about it because they have different properties and they convey to our intuitive sense different information. Okay, so in general though, if something is rare, there's not going to be that big a difference between the risk and the odds. But when something is a common condition, there can be a very big difference between the risk and the odds. So you have to A, be very careful what you're talking about, and B, make sure that your potential audience, readership, or whoever knows what you're talking about. One of the common mistakes that I see, and I don't blame them because I've made this mistake, so of course I'm more forgiving of it, is mixing up odds and risk. Okay. So now, once we're thinking just about risks, we have to understand the difference between the risk difference and the risk ratio. The risk difference is an absolute measure. The risk ratio is a relative measure. It compares two risks. Okay? So risk difference is the easiest one, and I think that's part of the reason that the Cochrane people like it. So you compute the risk in the treated group, you compute the risk in the control group. Okay, so again, it's people with it minus everyone who could have had, or could have divided by whoever could have had it, and people who don't divided by everyone who could have, and and the risk differences, you just subtract the risk in the treated group from the risk in the control group. So in this case, 0 means no difference. Okay. So if going back to my original example, there, okay, the risk difference between the treated group and the control group is minus 0.05. The risk ratio, you compute the risk in the treated group, you compute the risk in the control group, and the risk ratio basically divides one risk by the other risk. Okay, I find that dividing risks always confuses people. There's a theory in industrial and organizational psychology called equity theory, where you're also comparing two ratios, and people just get confused all the time. But when you're dividing, right, if you divide one thing by itself, right, you get 1. So with a risk ratio, 1 means no difference. So risk difference means 0 means no difference between the groups, and a risk ratio, 1 means no difference between the groups. When the risk ratio is above 1, it means the risk is higher in the treated group than in the control group. Okay? And here, if we look at the same numbers we found before with a risk difference of minus 0.05, we found the risk ratio is 0.5. Okay? So if people get those things confused, it could make quite a difference. Okay? And I'll show you an example. And so, of course, people like pharmaceutical companies and canning researchers of all sorts will often display the index that makes their hypothesis supported, or it makes their product look more effective or more desirable. And so you really need to know, even just as research consumers, what is actually, what's being displayed. One of the problems with the risk ratio is that it's not, what's the word, transitive. So if we talk about the risk ratio, right, we can get a where you have twice the risk in the control group of, let's say, whatever terrible disease it is, compared to the treated group, right? But you only have 10% risk even in the control group, okay? So you need to kind of know what the actual risk is before the risk ratio makes any sense to you, or I think makes any sense. So you can double the risk of something, but if it's a pretty rare event, you're still very unlikely to get it, okay? And people misunderstand those things, or the people who also don't understand the danger of false positives with different kinds of tests, like mammograms and prostate screenings and things. Okay. In general, with risk ratios and odds ratios, we actually do the calculations in log form. We don't operate directly on the risk ratio or on the odds ratio, but then we can convert it back to the non-log index when we're actually reporting the findings. But because people often like, one of the benefits of using the log, is that 0 means 0 difference. I think people have a hard time getting their heads around 1 means 0 difference. Okay. So if you want to do a meta-analysis using risk ratios, what you would do is you would extract the data from the 2x2 table for each study. You would compute the risk ratio on your own. You would convert the risk ratio to the log risk ratio, and then you would actually perform your meta-analysis on the log risk ratios. You get a summary log risk ratio, and then you back convert it into the summary risk ratio. You can't do the operations directly on the risk ratio for statistical reasons that you are not going to want to know about. But okay, odds ratios. Okay, you compute the odds of the treated group, and remember odds have to do with the people who got it versus the people who didn't, right? So you compute that in the treated group, you compute that in the control group, and then again, you divide the odds in the treated group by the odds in the control group. And again, the odds ratio, no difference means 1. When we use log odds ratios, the log transformation makes 0 mean 0 difference. So in our case, we're going back to the headache example. The odds ratio of getting a headache, given that you were in the treated group, is 0.47, which means that you're far less likely to get the headache if you have the treatment. Okay. Again, same thing as with the, whenever you see the word ratio, you should know that you have to put it into log form first. Do the operation, and then summary, and then convert it back convert it into the odds ratio. So you're going to have a choice. If you actually have the data in 2x2 form, you're going to have the choice of whether you want to calculate the risk ratio, the risk difference, or the odds ratio. Okay, and I want to show you an example again of why this matters. How many of you have heard of Avandia? Anybody? Okay, so Avandia was a diabetes medication that apparently was very good at controlling diabetes, but apparently had some adverse cardiovascular effects in the form of heart attacks, heart failure, and I believe stroke too. Okay? And there was actually a meta-analysis done on Avandia. It was actually done using our program, which led some journalists to call up Michael and ask him to comment on this whole meta-analysis. But in any case, let's assume that if every diabetic in the United States who had been taking Avandia were given a different pill, okay, let's call it Actos, then we would, this is reported in the Times, that about 500 heart attacks and 300 cases of heart failure would be avoided every month. Okay? Does that sound like a lot? Right? Okay. Okay. So I want you to look at that. This phrasing, this framing. If every diabetic now taking Avandia were given this pill named Actos, about 500 heart attacks and 300 cases of heart failure per month would be averted. Okay, and based on these reports, the FDA actually banned the use, or restricted it, I should say, because of their concern about heart attack risk. And you have to, like, sort of get special, permission from your doctor to be able to use it. Okay? Now, if we wanted to look at the risk ratio, the risk ratio was 1.43, which meant that if you took Avandia, your chances of dying from a heart attack or heart failure increased by almost 50%, right? However, if we wanted to look at the risk difference, it basically was 0.005, which basically said that your chance of dying from a heart attack goes up from 1 in 1,000 to 1 in 1,000. Okay? So, framed one way versus another, you might say, well, I don't want to increase my chance of dying by 50%. versus, well, you know, if my chance of dying is only 1.5 out of 1,000, and this is such a better drug for me in all sorts of other ways, I still think that I might want to take this medication. And so the people who were reporting their meta-analysis used the risk ratio, and the Times picked up on it, right? And it's not inaccurate, okay? It's one legitimate choice of an effect size index. But they didn't really mention what the baseline risk was, and baseline risk is something that you really want to know when you're talking about changes in that risk. So here's a handy-dandy little cheat sheet for the main differences between these three binary effect sizes. The risk difference and the odds ratio are both absolute measures, whereas the risk ratio is a relative measure. The odds ratio makes people's heads hurt if they're not statisticians, so you probably, it doesn't have like an intuitive meaning you can just grasp. The biggest problem with the risk ratio, which I started saying before and got distracted, is that the probability of success and the probability of failure are not reciprocal or transitive. So the way you frame your question, does it increase head pain or does it decrease head pain, will really change what the ratio looks like. And furthermore, the weights that each study will get will vary depending on whether you're looking at sort of positive versus negative phrasing. So a lot of people feel that that makes it a very undesirable index to use. Okay, Cochrane likes the risk difference. Okay, it's easy to compute. It is an absolute measure. It's easy to convert to number needed to treat, which is something that practicing physicians always want to know about. But it really is more variable than the risk ratio or the odds ratio across different populations, and also when the baseline risk differs across populations. So that's something that you really need to keep in mind. And I know when Cochrane's dealing with summary of results tables, there's this whole debate about which baseline risk to use. So the baseline risk might not only vary from study to study, but it could also then vary a third time in terms of the specific population you, as a clinician, are trying to use the findings for. Since I'm not a physician, I'm not going to get further involved in that conversation.
In the summary findings tables, you can specify one baseline risk if you think that's important for clinicians to know.
But how do you choose them?
I guess based on what's prevalent in clinical practice, if there's a low baseline group versus a high risk baseline group.
Okay. That's useful to know about. Correlations are basically where my background is, because we often use observational studies where we're not actually manipulating anything, but we're capturing pre-existing individual differences. But anytime you're basically doing any kind of survey, and you're not manipulating, you don't actually have a treatment, you're probably going to want to use the correlation. Okay. As in some of the other measures we looked at with correlations, we don't actually do the meta-analysis on the correlation, but we convert it to something called the Fisher R to Z transformation. Fisher C is not the same C as in the Z-score, though, so don't think it's the same thing. It's a variance stabilizing transformation because with traditional correlations, the variance is actually correlated with the size of the correlation, and you don't want that to happen. because we're concerned about the variance. So we use Fisher Z, we do all the work in Fisher Z, we get a summary of Fisher Z, and then we back transform it into a correlation. Okay. I want to say a little bit about effect size, conventions. Jack Cohn, famous social science statistician who essentially was the father of power analysis, was trying to get people to move away from statistical significance testing and to focus more on effect sizes. So he said, based on my knowledge of my corner of social psychology, here's what seems to be a small effect, D of 0.1, standardized mean difference of 0.1. Here's a medium effect, standardized mean difference of 0.3. Here's a large effect, standardized mean difference of 0.8. And somehow that just became like gospel truth, like God handed it down together with the Ten Commandments. And people will talk about whether they got a small, medium, or large effect in fields very far distant from Cohn's corner of the world. And I keep thinking that this poor man, if he's buried, is, rather than cremated, but he's be turning over in his grave, because he really was trying to be very careful that I'm just trying to get the ball rolling, I'm trying to get the conversation started, please do this for your own field. And instead, people get into like fights, over this effect size stuff. So I'm going to tell you what he would have told you, which is before you think about small, medium, or large, it's like the difference between shoe size and hat size, right? If you have a size 9 foot, doesn't mean you have a size 9 hat, and a size 9 for a hat might be way bigger relative to hat sizes than a size 9 shoe would be for feet sizes. So you really need to understand deeply what would be a clinically meaningful difference in your field, in your research question, and judge small, medium, or large there. And don't import the notion from somebody else's discipline. Nobody but people who are the experts in a particular clinical area can really make an informed decision about what a small, medium, or large, or meaningful in general, effect would be. Okay? So don't get sucked into the effect size wars. A very long time ago, there was a study, I think done by Rosenthal, also relating, taking an aspirin a day on preventing heart attacks. And if you look at the actual effect size, it would be considered trivially tiny by Cohen's rules, but given how many people actually are trying to, taking aspirin as an attempt to reduce cardiovascular disease, it still translates into thousands of lives saved. Okay, so metric matters, and effect size varies from substantive research question to substantive research question. Okay, and we don't want to ossify them based on, and forget that these are human decisions that can be altered based on cumulative experience. Any questions about this part? Okay. I'm going to skip this part. Okay. So now I want to talk about how we actually do the meta-analytic computations, how we actually get to our meta-analytic results. What the rule page you're looking for, I guess, right? Okay. So basically, even when studies have the exact same true effect size, so let's say you were God and you were looking down the mountain, right? And you knew that these two studies had exactly the same effect size. Because we're sampling, we're not looking at entire populations, we're always grabbing samples, there's going to be variation due to sampling error. Okay, so if we reach our hand in a bag of multicolored marbles and pull out a handful, it's not going to necessarily represent the true proportion in the bag. Okay, and if we grab two handfuls and they differ from each other, if we knew that we grabbed them from the same bag, we wouldn't have the problem. But in fact, in research, we end up with two handfuls, and the decision is, do they come from the same bag or not? Okay, everybody with me on that? So in this particular case, we have two studies where the true effect is the same, but because of sampling error variation, the observed effect in study 1 and the observed effect in study 2 look different. Okay? And our job as meta-analysts essentially are to decide whether these two studies differ just because of random sampling variation, or whether it reflects true differences in effects in the two studies. Okay? So what we want to do is we actually compute weights based on the variance in the study, or actually based on the inverse of the variance. So if it's a larger study, which therefore has, based on the laws of sample theory, is going to be a better estimate, we want it to have more weight than a study based on a small sample where we know that the estimate is likely to be further off from the true value. Right? So you all know the basic idea that small samples are more likely to be weird and not representative of their population value than large samples are. So essentially, think of this as weighting them by the likelihood of them being weird or aberrant values. Okay? So each study gets a weight that's based on the inverse of the variance, okay? Also known as precision. If those terms hurt your head, you can think of it roughly as sample size. So larger studies carry more information value. Okay? And let me demonstrate that for you. Let's say we have a single study. It has 50 people in the study, and the study produced a result of the treated group being half a standard deviation better than the control group. Okay? This is going to be the confidence interval based on one study, and if for some weird reason we decided to call that a meta-analysis, it would look exactly the same as the one study. We add a study. Okay? Same exact results, miracle of miracle, same sample size, the study looks the same, but if we now look at the summary, we have a meta-analysis of two studies now, okay? The mean effect is the same, but the precision of the estimate, the confidence interval around the effect has shrunk. 3 studies, 4 studies, okay, 5 studies. See what happens to the confidence interval? So that as we combine studies where the effect is identical or consistent, except for sampling error, we get a more and more precise estimate of the mean effect. So here the mean hasn't changed at all, but our confidence that that's the true representation of the mean of the population has increased considerably. Okay? Now, if you want to see how we would work that out in terms of how we would weight the study, you can see that in this case, each study because it's exactly the same size, carries the same amount of weight. What we would do is this is basically the weight times the variance, and what we do is we take the sum of the weights and divide it by, well, essentially, put it this way, we compute a sample size weighted mean. We can also then compute the variance around the mean and the standard error around the mean, and then we will have the mean for the summary and the standard error for the summary. Okay? So we've essentially because the precision changes, the p-value also changes. So with one study, we had a non-significant p-value. With two studies, we're already reaching significance. As the amount of information increases, our confidence that this effect was not due to chance gets stronger and stronger and stronger. Okay, and let's look at this particular three-study meta-analysis. They basically had one study that had a standardized mean difference of 0.57, another one that had a standardized mean difference of 0.75, and a third one that had 0.57. So our summary effect was 0.62. Okay, it's clearly significant, although none of the individual studies were. And these statistics, basically, I-squared tells us that all of the that none of the variation that we observe across the three values is actually due to true variation between studies. It's due to sampling error variance. And if we wanted to do a significance test on the amount of variability across the studies, we would find that it has a very low p-value. In other words, this is a test that the differences across the studies are due to true differences. And it's clearly not significant there.